Hello and welcome. My name is Franz Polster. This is the first of 3 videos on the subject of exponential approximation. The topic here is the theory of exponential approximation. The very first question, of course, is what is exponential approximation all about? As the name may already suggest, exponential approximation is about approximating continuous functions by exponential sums. These are sums of n terms, ai times e to the ti times x, with real coefficients ai and ti. For the moment, let us call this set V. So, as a first preliminary definition, given a real interval I and a continuous real function f, the task consists in finding an element E of V such that the Chebyshev norm of the difference function f minus e on I is minimal with respect to all elements of V. Or, in other words, we look for coefficients ai and ti such that E has this property. A function with this property is called a best approximation of f with respect to V on I. Notice, with the coefficients ti being a factor in the exponents, this is an instance of nonlinear approximation. This video aims to present the main results of the theory of exponential approximation. In particular, it deals with the issues of existence, uniqueness, and the properties characterizing best approximations. Numerical methods will be dealt with separately in my videos Direct Methods and Iterative Algorithms. As an outlook, I am planning videos featuring programs implementing those numerical methods. And finally, before getting to the subject proper, a few words on how this project came into existence. It all goes back to the work I did in the early 1970s at the mathematics department of the University of Erlangen for my Diplomarbeit, which in the following will be referred to as T1. Back then, the tools were mainframe computers, punch cards, plotters, typewriters, and the like. When the COVID pandemic and associated lockdowns came upon us, I decided that instead of sitting idly at home and watching TV, it might be worthwhile to rewrite T1, which in the following will be referred to as T2, and also to develop stable, user-friendly implementations of the algorithms instead of the more or less quick and dirty programs of 1973, using the technology of today: PC, high-resolution screens, graphic software, etc. T1 and T2 are available in the web at this address. These are the conventions and notations used in the following. I denotes a real interval. Ci is the set of continuous real functions on interval I. This is the Chebyshev norm of function f on interval I. And this stands for the degree of either a polynomial or an exponential sum. The latter will be defined in the course of this presentation. And this is the abbreviation for with respect to. Let us start with the issue of existence of best approximations. This is the preliminary definition given earlier. Unfortunately, it turns out that there is a deficiency with this set V, in that, in general, the existence of a best approximation cannot be guaranteed. To this end, Meinardus proved for function f(x times e to the x) with n equal to 2 that every environment of f contains an element of V, while f, however, is not an element of V. You find the proof in T2. As a consequence, in order to ensure the existence of best approximations, set V must either be extended and or proper subsets of V have to be identified. This leads to the following sets of exponential sums. Shaded here is the set V of simple exponential sums considered so far. From now on, this set will be referred to as V sub n 0. This set V sub n is the wanted extension of V sub n 0. The coefficients ai are replaced by real polynomials pi, and the polynomials satisfy the condition that the sum of their degrees plus 1 is at most n. Then there are two subsets of V sub n 0. V sub n plus is the set of simple exponential sums where all coefficients ai are positive, while for V sub n minus all coefficients ai are negative. Without loss of generality, we assume that the terms of exponential sums are ordered in such a way that Ti is less than Ti plus 1. Before moving on to the existence theorem, two remarks. First, it should be pointed out that the arguments a are just a means of naming or identifying a specific exponential sum. In particular, a is not related to the ai's of the sums. Second, only when dealing with simple exponential sums of V sub n 0 and its subsets, a can, and in fact will, be considered a vector consisting of the coefficients ai and ti. We are ready now for the existence theorem by Schmidt and Werner. They have shown that for a continuous function f, there exists a best approximation with respect to each of the sets V sub n plus, and V sub n minus respectively. However, as Brass has shown, in general, there may exist more than one best approximation with respect to V sub n. But as we will see later, uniqueness holds with respect to V sub n 0 and its subsets. Since the respective uniqueness statements are tightly connected to the properties characterizing best approximations, we now proceed to the issue of characterization. The concept of alternant of a function is instrumental for the characterization of best approximations. An alternant is a set of extremal points of function f where a point x of interval I is called an extremal point if the absolute value of f of x is equal to the norm of f on I. And f has in I an alternant of length n if there are n ordered extremal points xi such that the signs of the values of f at extremal points xi and xi plus 1 are different. Such points are referred to as alternate points of f. We say that f has a positive alternate of length n if f at alternate point xn is positive, and analogously, f has a negative alternate if f at alternate point xn is negative. Here, as an example, a positive alternate of length 7. This is the graph of function e, which happens to be the error function of the best approximation of function 1 over 1 plus x with respect to v sub 3. And this is the norm of e on I visualized by these dashed lines. As you can see, error function e has 7 local extrema, 1, 2, 3, 4, 5, 6, and 7, at which its absolute value is equal to its norm with the signs alternating. These are the alternate points x1 through x7. With e at x7 positive, this is a positive alternate. Also, we need the following terminology. The degree of an exponential sum is the sum of its polynomial degrees plus 1. And L is the length of E if the degrees of its polynomials are greater than or equal to 0. Note, first, the length of an exponential sum is less than or equal to its degree. Second, for simple exponential sums, length and degree are the same. And finally, the length of an exponential sum is the number of its non-zero summons. We are ready now to explore the properties of best approximations. For the most general case, that is approximation with respect to v sub n, Brass has shown that for exponential sum e of x with degree k and length L, the following statements hold. If the error function f minus e has an alternate of length n plus k plus 1, then e is a best approximation with respect to v sub n, and moreover, e is even the unique best approximation. On the other hand, if e is a best approximation with respect to v sub n, then the error function f minus e must have an alternate of length n plus l plus 1. Remember, length L is less than or equal to the degree k. So, the alternate in statement A, which entails uniqueness, is at least as long or longer as the one in B. For the set V sub n 0 follows as a corollary that an alternate of length n plus l plus 1 is a necessary and sufficient condition for a best approximation with respect to V sub n 0. In particular, when the best approximation with respect to V sub n 0 has length n, which is the usual situation when computing approximations, then the length of the alternate is 2n plus 1. And part B of the corollary says that a best approximation with respect to V sub n 0 is the unique best approximation with respect to both v sub n0 and v sub n. Similar statements hold for the subsets of v sub n0. Let us start with v sub n plus. A best approximation E with respect to v sub n plus is unique, and it is also the unique best approximation with respect to v sub L0 and v sub L. And these are the corresponding statements with respect to v sub n minus. Just flip the signs in the shaded areas. More elaborate is the characterization of the best approximations with respect to v sub n plus. For the case that the length L of E is equal to n, there is no difference. An alternant of length 2n plus 1 is a necessary and sufficient condition for the best approximation with respect to v sub n plus. But if the length is less than n, it is sufficient for the length of the alternant to be only 2l plus 1 if in addition the alternant is a negative one. And as a corollary, also by Bress, if the length of a best approximation is less than n, then it is the best approximation also with respect to all sets v sub I plus for I greater than L. And if the length of the best approximation is exactly n, then for all I less than L, the best approximation with respect to v sub I plus has length I. Note, for the approximation by exponential sums with positive coefficients ai, this means that if ei denotes the best approximation with respect to v sub I plus, then there may be an integer k such that up to this k, the best approximations e sub I are mutually different because their lengths are different, and from k on, the best approximation possible is always ek. In other words, longer exponential sums with positive coefficients ai will not be better approximations. Again, corresponding statements hold for v sub n minus, just flip the signs in the shaded areas. So much about the characteristics and the uniqueness of best approximations. We now turn to the question of, given the best approximation, what are the properties of better approximations and where to look for them? For the best approximations, with respect to the set v sub n plus, Bress has shown that if the best approximation with respect to v sub n minus 1 plus is not the best approximation with respect to v sub n plus, then better approximations must be elements of v sub n plus only. And moreover, the coefficients ti of the best approximation lie in between pairs of successive coefficients si of better approximations. This may be a useful clue as to the coefficients si when calculating better approximations. Again, as you will expect, corresponding statements hold for v sub n minus. Just flip the signs in the shaded areas. A second, more general theorem about where to look for better approximations relies on the concept of sign classes. To this end, exponential sums are assigned so-called sign vectors in a recursive way. An exponential sum consisting of exactly one term is assigned the sign vector sign of e with these n plus 1 components, where s is the sign of an, with the usual definition of the sign of a real number. And the sign vector of a sum of exponential sums is the concatenation of the sign vectors of the summons. As an example, this is the sign vector of an exponential sum with 3 summons EA, EB, EC. With sign vectors are associated sign classes. For a sign vector S, the sign class of S in V sub n consists of all exponential sums E in V sub n, where the sign vector of E is S, or the sign vector of E can be derived from S by removing components from S. The sign class of S in V sub n0 contains only simple exponential sums with a sign vector S. Examples: with n equal to 3 and this sign vector is equal to S, and the sign vectors of these two exponential sums can be derived from S. Therefore, these 3 exponential sums are elements of V sub 3 S. This is not the case for this exponential sum. Its sign vector cannot be derived from S. Brass has shown that for the best approximation with respect to V sub n0 EA with degree n, the sign vectors of any better approximation EB consists of at least as many positive and negative components as the sign vector of EA. This means that the sign vector of a better approximation can be constructed by adding positive and or negative components to the sign vector of the best approximation at hand. In fact, this theorem by Brass tells us how to construct sign vectors for sign classes which contain better approximations. Let EA with degree k be a best approximation with respect to V sub n-1 0, but not V sub n. And let the error function f minus EA have a positive alternant of length n plus k. S be a sign vector with n components which satisfies these two conditions. First, removal of n minus k components Sik yields the sign vector of EA. Secondly, the signs of the components removed are alternating, and the last component removed is positive. Then the sign class associated with sign vector S contains a better approximation. Or the other way around, this theorem says that given the best approximation with respect to V sub n-1 0, adding such components as ik to its sign vector results in a sign class which contains a better approximation. If k is equal to n-1, an estimate for the number of sign classes with better approximations can be derived. With k equal to n-1, this theorem says that if the sign vector of the best approximation has k minus negative components, then there are k minus plus 1 different sign classes with better approximations. Note, this is a minimum, there may be more. Again, corresponding statements hold for negative alternants. Just flip the signs in the shaded areas. To demonstrate the application of this theorem, we use the previous example with the best approximation of function 1 over 1 plus x. Here, k is equal to 3, n is 4. This is the sign vector of the best approximation. It has no negative components. The alternant of the error function is a positive one. It has length 7, which is k plus n. According to the theorem, there exists at least one sign class in V sub 4 with better approximations. The component to be added is plus 1, thus this gives us this sign vector and sign class. Let us now turn to the last topic, which is local minima in V sub n. Since in general there are more than just one best approximations for a function f with respect to V sub n, numerical methods for the calculation of best approximations may have to deal with local minima. E prime is called a local minimum of f in V sub n if there exists an environment U of E prime such that the norm of the error function f minus E prime is less than or equal to the norm of the error function f minus E for all E in U. And this is the corresponding definition for the set V sub n 0. Werner has shown that a local minimum of f in V sub n 0 is also the best approximation of f with respect to V sub n 0. And even better, if a simple exponential sum is a local minimum of f in V sub n, then it is also the best approximation with respect to V sub n. This means that local minima in V sub n, which are not best approximations, cannot be simple exponential sums. And an algorithm that finds local minima with respect to V sub n 0 also finds best approximations with respect to V sub n 0 and V sub n. This concludes the presentation of the theory of exponential approximation. As has been pointed out in the introduction, the documents referenced are available in the web at this address. Thank you for your interest and endurance. You are welcome to move on to the videos on numerical methods and algorithms. Goodbye and see you there.